Hello there, and welcome to The Sleepy Scholar. Tonight's journey takes us down beneath the gentle surface of the waves into the warm, sunlit waters of the living ocean to explore the majestic world of coral reefs. There is a world waiting just below the horizon of the air, a vast, submerged kingdom painted in colors that seem borrowed from a dream. Here, great structures rise from the sea floor, not built of stone or steel, but woven from life itself. They are the planet's hidden gardens, cities of countless small, patient architects, bathed in a light that filters down from above, dancing and shimmering with every movement of the tide. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. The Great Barrier Reef is the largest living structure on Earth, so vast that it is clearly visible from space. Our planet is adorned with monumental structures, from towering mountain ranges to vast canyons, most of them sculpted by the slow, immense forces of geology. But off the northeast coast of Australia, there is a structure of a different kind, one that rivals the scale of mountains, but was built entirely by the patient labor of tiny, living beings. This is the Great Barrier Reef, a sprawling, interconnected system of over 2,900 individual reefs and 900 islands. It stretches for over 2,300 kilometers, or more than 1,400 miles, covering an area of approximately 344,400 square kilometers, or 133,000 square miles. This is not a single, continuous wall, but a vast and complex labyrinth of coral formations. Astronauts orbiting high above the Earth can look down and see its intricate, milky blue patterns tracing the continental shelf, a vibrant living fringe separating the deep ocean from the coast. To see it from such a height is to understand the true power of persistence, a reminder that the smallest lives, joined in common purpose over unimaginable time, can build a monument that touches the heavens. Coral reefs are often called the rainforests of the sea because of their incredible biodiversity. On land, the tropical rainforests are celebrated as the planet's hotspots of life. Teeming with a dizzying variety of species in the ocean, this same vital role is played by the coral reefs. Though they occupy a tiny fraction of the ocean floor, less than 1%, they provide a home for a staggering number of marine species. It is estimated that coral reefs support around 25% of all known marine life. This includes over 4,000 different species of fish, hundreds of coral species, and countless other invertebrates like crabs, clams, sea stars, and sponges. The reef's complex, three-dimensional structure is the key, providing an endless array of nooks, crannies, caves, and ledges. These spaces serve as nurseries for the young, hiding places from predators, and platforms for hunting, making the reef a complete, self-contained city. The reef does not hoard this life. It generously offers itself as a safe haven, a vibrant, crowded, and harmonious metropolis, where countless stories of evolution are written in the language of color and form. Although corals get most of their food from algae during the day, they are also active predators at night. During the sunlit hours, the coral reef appears to be in a state of quiet, sun-bathing repose, with the polyps largely retracted to allow their internal algae to gather the maximum amount of sunlight. But when darkness falls upon the ocean, the reef awakens, and its true nature as an animal is revealed. Under the cover of night, the coral polyps emerge from their stony cups, extending their delicate, stinging tentacles into the passing currents, creating a soft, fuzzy appearance on the coral surface. These tentacles are armed with specialized stinging cells called nematocysts, the same weapons used by their jellyfish cousins. As tiny drifting animals, collectively known as zooplankton, brush against the tentacles, they are paralyzed and drawn into the polyp's central mouth, allowing the entire reef to become a massive, filter-feeding entity. This dual existence is the secret to the coral's success. It is both a patient farmer, tending its internal gardens of light, and a silent hunter, waiting for the gifts of the night tide. Geologists and biologists classify coral reefs into three main types: fringing reefs, barrier reefs, and atolls. While we often speak of the coral reef as a single concept, these living structures take on distinct and magnificent forms, each one shaped by the geological stage of the landmass it embraces. This classification was first proposed by Charles Darwin, who observed how islands and reefs change over immense stretches of time. The first type is the fringing reef, which grows directly from the shore, attached to the coastline of a continent or a young volcanic island. The second type is the barrier reef, which is separated from the shore by a wide, deep lagoon, and is often an older, larger structure that has grown upwards as the nearby landmass slowly subsided. The third, and perhaps most poetic form, is the atoll, a ring of coral that encloses a central lagoon, which is all that remains of a volcanic island that has long since sunk completely beneath the waves. These three forms tell a story of geological time, a slow, majestic dance between the land rising from the Earth's fire and the sea that seeks to reclaim it, with the coral building a living crown upon the sinking mountain. Many corals reproduce in a spectacular, synchronized event known as mass spawning. For most of the year, the reef is a place of steady, quiet growth. But for a few precious nights each year, this calm is broken by an extraordinary explosion of life. This event is tied to the ancient, powerful rhythms of the planet, triggered by the cycles of the moon and the precise warming of the water. When the conditions are perfect, entire sections of the reef, sometimes spanning hundreds of miles or kilometers, begin to spawn in unison. The coral colonies release massive quantities of tiny buoyant bundles containing both eggs and sperm. These colorful spheres, often pink, red, or orange, rise slowly toward the surface, turning the water into a thick, swirling, upside-down blizzard of potential life. This mass synchronization is a vital strategy. It overwhelms predators, ensuring that enough bundles survive to fertilize and create new coral larvae. This event is the reef's ultimate act of faith, a simultaneous release of hope into the vastness of the ocean, a galaxy of tiny stars ascending towards the moonlight. After spawning, tiny coral larvae, called planulae, may drift for weeks in search of the perfect place to build a new reef. Once fertilization is successful in the sunlit surface waters, a new life begins as a tiny, free-swimming larva. This creature is barely visible to the naked eye, a small, pear-shaped organism covered in tiny hairs, or cilia, that it uses to propel itself through the water. It is now an orphan, adrift on the open ocean currents, carrying the immense responsibility of founding an entirely new colony. This drifting phase can last for days or even weeks, as the planula searches not just for any hard surface, but for a very specific set of conditions. It is guided by chemical cues in the water, particularly the presence of certain types of crust-like coralline algae, which signal a stable and healthy environment. When the larva finds the perfect spot, it cements itself permanently to the substrate and begins the process of metamorphosis into a single, founding polyp. This tiny voyager, after its long and perilous journey, finally ends its wandering and chooses a home, becoming the first quiet architect of a structure that may one day grow to the size of a mountain. Coral polyps are animals, not plants, and they are the tiny architects of the vast, stony structures we call reefs. When we gaze upon a reef, we see what appears to be a submarine garden, full of branching trees, delicate fans, and rounded boulders, all swaying gently in the current. It is easy to assume these are exotic forms of marine flora, soaking up the sunlight like their terrestrial counterparts. But this entire sprawling city is an animal kingdom, a vast colony of interconnected beings. Each individual coral polyp is a simple creature, often just a few millimeters, or a fraction of an inch, across, related to jellyfish and sea anemones. It is essentially a tiny tube-like body with a mouth at one end, encircled by a ring of stinging tentacles. They build their hard protective skeletons by drawing calcium carbonate from the seawater, creating a small cup to live in. A coral head is actually a massive colony of thousands, or even millions, of these genetically identical polyps, living together, sharing nutrients, and fusing their skeletons over generations to build the immense structures we recognize. These tiny architects, each one a soft, vulnerable creature, demonstrate the profound power of collective effort, patiently secreting their stony homes layer by layer until their shared endeavor becomes a fortress of life that can withstand the power of the ocean. The brilliant colors of coral do not come from the animal itself, but from microscopic algae living inside its tissues. The spectacular palette of a coral reef, the vibrant greens, electric blues, and fiery reds, is perhaps its most defining and hypnotic feature. Yet the coral polyp itself is naturally translucent, almost clear, and its stony skeleton beneath is a stark, chalky white. The color, the very vibrancy that defines the reef, is a gift from a microscopic tenant called zooxanthellae. This relationship is a perfect ancient symbiosis. The clear coral tissue provides the algae with a safe, protected home and exposure to the sunlight it needs in the shallow water. In return, the algae perform photosynthesis, just like a plant, converting sunlight into sugars and other nutrients, generating up to 90% of the coral's total food supply. This internal food source is what allows corals to thrive in tropical waters that are often surprisingly low in nutrients, and the specific pigments within the algae are what we perceive as the coral's beautiful color. This partnership is the engine of the reef, a testament to shared existence, where the coral offers shelter and the algae offers life itself, painting its host in the colors of gratitude. When corals turn stark white, an event known as bleaching, it is a sign of profound stress. In a healthy reef, the colors are a symphony of life, a sign that the symbiotic partnership between polyp and algae is in perfect balance. But when the water becomes too warm, even by just 1 or 2 degrees Celsius or a few degrees Fahrenheit, for an extended period, that delicate relationship fractures. This warmth causes the zooxanthellae algae to produce molecules that are harmful to their coral host. The coral, sensing this distress, makes a desperate choice for survival and actively expels the algae from its tissues. As the colorful algae are ejected, the coral loses its primary food source and its vibrant pigmentation, revealing the stark white calcium carbonate skeleton through the polyp's now clear tissue. A bleached coral is not dead, not yet, but it is starving and deeply vulnerable. The ghostly white reef is not a tomb, but a pale flag of surrender, a quiet alarm bell ringing through the ocean, the coral's last plea for the waters to cool, so it may welcome its colourful partners back into its empty home. Coral reefs serve as natural, living breakwaters, protecting coastlines from storms and erosion. From the shore, the ocean can appear as a vast, untamed force, especially during powerful storms, when the energy of large waves can devastate coastal communities. But for millions of people living in the tropics, there is a silent guardian standing watch just beneath the waves, a fortress built not of concrete, but of life. This guardian is the coral reef. The reef's complex, irregular, and solid structure is exceptionally effective at absorbing and dissipating wave energy. As massive storm waves roll in from the deep ocean, they crash against the outer edge of the reef, and their force is broken, allowing much calmer water to reach the shore. It is estimated that healthy coral reefs can absorb up to 97% of a wave's energy. This natural defense is more effective and far more self-repairing than many artificial seawalls. The reef stands as a patient shield, a living barrier that embraces the land, holding the raw power of the ocean in a stony, protective caress. The massive, ancient structures of a reef are built with incredible slowness, with some corals growing less than an inch per year. We live in a world defined by rapid change, making it difficult to comprehend a timescale of creation that moves with the pace of geology itself. The coral reef is a monument to this kind of patience, a structure that measures its age not in decades, but in millennia. The growth rate of coral varies by species. The faster-growing branching corals, like staghorn, might grow upwards of 10 to 20 centimeters, or about 4 to 8 inches per year under ideal conditions. But the massive, boulder-like corals, the great brain corals, are far more slow and deliberate, often growing less than 1 centimeter, or well under half an inch per year. This means that a large boulder coral head, one that stands taller than a person, may be many hundreds or even thousands of years old. These ancient beings are the elders of the sea, living historians that have recorded centuries of ocean life in their stony skeletons, living cathedrals built by the unceasing, quiet devotion of countless generations. The beautiful white sand beaches found on many tropical islands are largely produced by parrotfish eating and excreting coral. Lying on a soft, white sand beach is a quintessential image of tropical paradise, but the origin of this sand is often biological. It comes from the daily work of one of the reef's most colourful and industrious residents, the parrotfish. This fish is named for its beak-like mouth, which is a fusion of teeth strong enough to bite directly into the hard calcium carbonate skeleton of the coral. The fish is scraping off the nutrient-rich algae that grows on the coral's surface, and in the process, it scrapes away chunks of the coral skeleton as well. This material passes through the fish's specialized digestive system, where internal teeth grind it down into fine particles to extract the algae. The indigestible coral skeleton is then excreted as a fine plume of clean, white sand. A single large parrotfish can produce hundreds of pounds or kilograms of sand every year. This creature, in its quest for food, becomes an accidental sculptor, the reef's own recycling system, turning old stone back into new earth. While we associate coral with warm, sunny waters, there are also deep-sea corals that live in total darkness and near freezing temperatures. The image of a coral reef is almost inseparable from that of shallow, sun-drenched tropical lagoons, as we think of them as creatures of light. But the deep ocean, a realm of perpetual night, far beyond the sun's reach, holds its own magnificent secret gardens, These are the cold water corals. They can be found in waters as deep as 2,000 meters or over 6,500 feet, where temperatures can hover near 4 degrees Celsius or 39 degrees Fahrenheit. Unlike their shallow water relatives, these corals do not host symbiotic algae, as there is no sunlight. Instead, they are entirely dependent on capturing food, using their tentacles to filter tiny plankton and organic particles that drift down from the richer waters far above. They grow even more slowly than tropical corals, yet they build massive, complex reef structures that are just as vital, providing habitat for deep-sea life. These deep reefs are the planet's hidden counterpart, a silent, pale city that thrives on the memory of the sun. A healthy coral reef is not silent. It is filled with a constant chorus of pops, crackles, and crunches. When we imagine the world beneath the waves, we often think of a silent, muffled realm. But if you were to submerge yourself and simply listen, you would discover that the reef is one of the noisiest environments in the ocean. This sound is not the call of fishes, but the sound of life in motion. The most dominant noise is a constant, frying-like crackle. This is the sound of thousands of tiny snapping shrimp hidden within the reef's crevices, which snap their specialized claws to stun prey or communicate, creating a tiny bubble that collapses with a sharp pop. Added to this chorus are the crunching sounds of parrotfish grinding on the coral and the rasping of sea urchins as they scrape algae. Scientists use hydrophones to listen to this acoustic signature, and the volume of the sound is a direct measure of the reef's health. A quiet reef is a dying one. The sound of a healthy reef is the audible heartbeat of a community at work. Corals are engaged in a constant, slow-motion battle with their neighbors for territory. The reef appears to be a harmonious, densely packed community, but this peaceful coexistence is an illusion. In reality, the reef is a battlefield where space is the most valuable resource, and the corals are locked in a silent, creeping warfare that unfolds over months and years. Corals have developed several ways to compete. Some simply grow faster, creating branches that rise above their neighbors to steal the precious sunlight. Others engage in a more direct chemical warfare. They can extrude long, digestive filaments from their stomachs and lay them upon an encroaching neighbor, slowly digesting the living tissue of the rival colony to clear a path. Some species also have specialized sweeper tentacles, which are extra long and loaded with stinging cells, used specifically to reach out and sting any other coral that gets too close. This silent struggle is not one of malice, but of necessity, the slow, deliberate dance of life asserting itself, a quiet but relentless negotiation for a place in the sun. A single starfish, the crown of thorns, can be responsible for devastating large areas of a coral reef. In the intricate food web of the reef, predators are essential for maintaining balance, but sometimes this balance can be catastrophically upset. One of the reef's most formidable predators is a large, multi-armed starfish covered in long, venomous spines. This starfish is a voracious coral predator. It feeds by climbing onto a coral colony and everting its own stomach out through its mouth, spreading it over the living polyps. It then releases digestive enzymes, liquefying the coral tissue and absorbing the nutrients, leaving behind only the white, dead skeleton. A single crown-of-thorn starfish can consume several square meters, or many square feet, of living coral per year. While they are a natural part of the ecosystem, periodic outbreaks can occur where their populations explode, and thousands of these starfish move across a reef like a slow-moving army, consuming almost everything in their path. This creature embodies the awesome power of nature's cycles, a pruning mechanism where creation and dissolution are forever intertwined. The complex chemical compounds found in coral reefs are a vital source for new life-saving medicines. Hidden within the tissues of the corals, sponges, and other reef-dwelling organisms is an invisible treasure, a vast untapped library of unique chemical compounds. These organisms have been engaged in chemical warfare and defense for millions of years, and the weapons they have developed are now being studied to fight human diseases because they are stationary. Many reef creatures cannot flee from predators, so they produce powerful toxins and antibiotics to defend themselves. Scientists have discovered compounds in reef organisms that show incredible promise. Some chemicals from sponges are used in anti-cancer drugs and antiviral medications. The coral's own skeleton has been used as a foundation for bone grafts, as its porous structure is readily accepted by the human body. The reef is, in effect, a massive, living pharmaceutical laboratory. It holds not only the secrets to its own survival, but potentially the keys to ours, a healing gift from the ocean, reminding us that its health is deeply linked to our own. The record for the deepest living photosynthetic coral belongs to a species found at over 165 meters, or 540 feet. Down, the partnership with sunlight-dependent algae tethers most reef-building corals to the shallow, sunlit surface of the ocean. We believed for a long time that this partnership could not exist in the ocean's deeper, dimmer twilight regions. However, scientists have discovered colonies of the coral Leptoceras thriving in the deep waters of the Hawaiian archipelago, at depths where the sunlight is less than 1% as strong as it is at the surface. The light that reaches this depth is a faint, ethereal blue. To survive here, both the coral and its algae have made remarkable adaptations. The coral grows in thin, plate-like sheets, a shape that maximizes the surface area for capturing every possible photon of light. The algae inside them possess specialized, hyper-efficient pigments designed to trap and use this faint, monochromatic blue light, allowing photosynthesis to continue in what we would perceive as near total darkness. This deep coral is a living solar panel, perfectly engineered by evolution to harvest the last fading whispers of the sun. The skeletons of large old corals contain growth rings, similar to trees, that serve as a precise archive of past ocean conditions. To understand the future of our climate, scientists must first look to the past, but reliable weather records only go back about 150 years. To see further, they must find a natural historian, a living creature that has been patiently recording the environment for centuries. The massive, slow-growing boulder corals are perfect for this. As they grow, they lay down new layers of their calcium carbonate skeleton, creating annual growth bands. By drilling a core sample from one of these ancient corals, scientists can unlock a year-by-year history of the sea. The chemical composition of each band is a direct reflection of the water it grew in. Scientists can analyze the isotopes of oxygen to determine the exact temperature of the water in that year, and trace elements can reveal patterns of rainfall, storm events, and even coastal runoff. These ancient corals are stone diaries, a perfect, unblemished memory of 1,000 forgotten summers, offering us their ancient wisdom. The world's largest artificial reef is the Oriskany Reef, created by the intentional sinking of a massive aircraft carrier. While natural reefs are built by the slow work of living polyps, humans have attempted to create new marine habitats by sinking large, stable structures to the seafloor. These artificial reefs can provide a new foundation for marine life, a clean, hard substrate in areas where the ocean floor is otherwise barren sand. In 2006, the United States Navy aircraft carrier, the USS Oriskany, was carefully and intentionally sunk in the Gulf of Mexico, off the coast of Florida. This enormous vessel, measuring over 900 feet, or 270 meters in length, came to rest upright on the seafloor at a depth of about 212 feet, or 65 meters. After extensive cleaning to remove all hazardous materials, the massive steel structure became a new instant habitat, and it has since been completely colonized by sponges, corals, and vast schools of fish. This great ship, once a vessel of human conflict, has been embraced by the ocean, transformed from a steel behemoth into a living sanctuary. The relationship between clownfish and sea anemones is a famous symbiosis, but it is the anemone, not the coral, that provides the home. We often picture the bright orange clownfish darting among the branches of a reef, but its true sanctuary is a creature that looks like a coral, but is a very different animal, the sea anemone. Anemones are related to corals, but they are solitary, soft-bodied polyps without a hard skeleton, and their tentacles are armed with a far more potent sting, designed to paralyze passing fish. The clownfish, however, has a unique defense. It develops a thick layer of protective mucus on its skin, a chemical camouflage that tricks the anemone into believing the fish is just another part of itself, preventing the stinging cells from firing. This immunity allows the clownfish to live safely within the anemone's lethal embrace, protected from all other predators. In return for this safe harbor, the clownfish is a meticulous housekeeper, cleaning debris from the anemone's base, and it may even lure other fish into the anemone's tentacles, providing a meal for its protector. This is a partnership of perfect trust, a small, vibrant fish finding a home in the one place the rest of the ocean knows to fear. The most widely distributed coral in the world is not a reef builder, but a small, solitary cup coral. When we dream of coral, we picture the vast, interconnected colonies of the tropics, the massive structures that form the Great Barrier Reef. But the true globetrotter of the coral world is a humble, independent creature. This solitary cup coral, belonging to the Caryophyllidea family, does not build reefs at all. It lives its life as a single, isolated polyp, building a small, stony cup for itself, often no larger than a small coin. It has freed itself from the constraints of sunlight and warmth that bind its colonial relatives. These hardy individuals can be found in almost every ocean, from the shallow, sunlit waters of the tropics to the crushing, frigid darkness of the deep-sea trenches, and from the Antarctic to the Arctic. They anchor themselves to any hard surface they can find, whether it be a rocky outcrop, the leg of an oil rig, or the hull of a sunken ship. This tiny animal is the ocean's quiet pioneer, a testament to the resilience of life, proving that even in isolation, it can find a foothold in the most unforgiving corners of the planet. Coral reefs have an arch rival in the ocean, the fast-growing macroalgae, or seaweed. The shallow sea floor is a realm of limited space, and two great life forms are in a constant, slow-motion struggle to claim it. The corals, which build stony cities, and the large, fleshy seaweeds, which grow in dense, leafy forests. In a healthy, balanced ecosystem, the corals hold the advantage. Grazing animals, like parrotfish and sea urchins, tirelessly mow down the algae, keeping the reef clean and allowing the corals space and sunlight to grow. But when this balance is disturbed, the seaweed can quickly gain the upper hand. If pollution introduces too many nutrients, like nitrogen and phosphorus, into the water, it acts as a fertilizer for the algae, causing it to grow with unnatural speed. At the same time, if overfishing removes too many of the grazing fish, there is nothing to keep the seaweed in check. The algae can then grow over the coral, smothering it, blocking the sunlight, and turning a vibrant, diverse reef into a murky, monotonous field of green. This is the reef's shadow self, a different kind of garden, one that waits patiently for the builders to falter so the meadows can reclaim the stone. The beautiful and complex patterns of a brain coral are a masterpiece of mathematical efficiency. Gazing down at a large, dome-shaped brain coral, you see a surface covered in long, winding valleys and ridges, a perfect, meandering labyrinth that perfectly mimics the folds of a human brain. This intricate pattern is not a simple decorative choice. It is a profound biological solution to a geometric problem. The coral polyp needs to maximize its surface area, both to catch food from the water and to expose its internal algae to the sun. As the colony grows, if it simply expanded as a smooth dome, the surface area would grow much more slowly than its total volume. By folding its surface, creating these meandering valleys, the coral is able to pack an enormous amount of living tissue and algae into a compact, strong, and stable shape. This pattern, dictated by the laws of physics and growth, is the most efficient way to build, a living example of how nature, as the ultimate engineer, always finds the most elegant and beautiful solution. Ocean acidification is a silent threat to coral reefs, as it makes it harder for polyps to build their stony skeletons. The ocean is a vast blue heart, absorbing a significant portion of the carbon dioxide that enters our atmosphere. But as it takes in this excess, the very chemistry of the water begins to change, a slow, invisible shift towards becoming more acidic. This change, known as ocean acidification, does not burn the coral, but rather it starves them of their building blocks. Coral polyps construct their skeletons from calcium carbonate, minerals they must pull from the seawater. As the water becomes more acidic, it holds fewer of the carbonate ions the corals need. The polyps must expend far more energy to build their homes, like a mason trying to build a wall with crumbling mortar. As the acidity increases, growth slows, and in extreme cases, the water can become corrosive, slowly and gently dissolving the existing reef structure. This is not a sudden, violent event, but a slow, quiet unraveling, as the very water that has always nurtured the reef turns against it, making the act of creation an almost impossible task. The loudest sound ever recorded from a coral reef was the sound of its own recovery. After a reef has been damaged, perhaps by a storm or a bleaching event, the process of its rebirth is announced by a specific and powerful sound as young fish and invertebrate larvae return to the reef to settle. They are guided by the sound of a healthy home. Scientists, in an attempt to understand this, have played recordings of healthy reefs through underwater speakers in dead or dying reef areas. They found that these sounds of life can actually attract new residents, jump-starting the recovery process. But the reef's own sound, the chorus of snapping shrimp and grazing fish, is the most powerful beacon. The return of this sound, a growing crescendo of pops and crunches after a period of silence, is the most hopeful song in the ocean. It is the audible proof of resilience, the sound of a community rebuilding itself. the reef's own voice returning as it calls its lost children home from the open water. Some corals are nomadic, capable of detaching from the seafloor and walking to a new location. We think of corals as the definition of a sedentary life, permanently cemented to one spot for their entire, centuries-long existence. But in the soft, sandy bottoms of some lagoons, where a solid foothold is hard to find, certain species of walking coral have evolved a remarkable independence. These mushroom corals, or fungidae, live as large, solitary, disc-shaped polyps, resting unattached on the sand. While they are often moved by strong water currents, they also possess a limited, slow-motion form of mobility by inflating and deflating their tissues with water, or by using their short tentacles. They can gradually inch their way across the seafloor. This ability allows them to escape from being buried by shifting sand, to move away from an aggressive neighbor, or even to slowly flip themselves over if they are overturned by a storm. This creature is the reef's gentle wanderer, a living stone that has learned to travel, reminding us that even a life built on patience can still possess a quiet, determined freedom. A specific species of goby fish forms a lifelong cooperative bond with a pistol shrimp, sharing a burrow in the coral sand. In the sandy plains surrounding the reef, life is exposed and shelter is scarce, a vulnerability that has forged one of the ocean's most charming partnerships. A small, industrious pistol shrimp, which is nearly blind, excavates a complex burrow in the sand, a safe bunker to hide from predators. However, its poor eyesight makes it dangerous to leave the burrow. Its partner, the watchful goby fish, has excellent vision. The fish stands guard at the burrow's entrance, while the shrimp uses its powerful claws to tirelessly maintain the home, clearing out sand and debris. The two are in constant communication through touch. The shrimp will always keep one of its long antennae on the fish's tail. If the goby senses danger, it gives a specific flick of its tail, and both creatures vanish into the burrow in a fraction of a second. The fish gains a safe, well-kept home, and the shrimp gains a pair of eyes, a perfect symbiotic union built on trust and a shared need for security. The deepest known coral reef ecosystem was discovered in 2018 off the coast of South Carolina, stretching over 160 kilometers or 100 miles. While we knew of deep-sea corals in small, isolated mounds, the discovery of a vast, sprawling reef system in the deep, dark waters of the Atlantic shifted our understanding of their scale. This newly mapped region, known as the Million Mounds area, is a vast, ancient landscape of coral mounds built by Lophilia pertusa, a cold-water reef-building coral. Some of these mounds are over 85 meters, or 280 feet, tall. This is not a sunlit garden, but a silent, cold, and utterly dark city, thriving at depths between 700 and 1,000 meters, or 2,300 to 3,300 feet. This immense reef, existing in a place we once thought was barren, survives entirely on marine snow, the faint drizzle of organic matter falling from the productive waters far above. It is a hidden, cold water equivalent of the Great Barrier Reef, a sleeping giant of a city that has been patiently growing in the dark for millennia. The structure of a coral reef is so complex that it follows mathematical principles known as fractal geometry. A fractal is a pattern that repeats itself at different scales, meaning the closer you look, the more complexity you find. Yet the pattern remains familiar. A coral reef is a perfect living fractal. From a great distance, you see the large-scale structure of the reef system, with its lagoons and outer crests as you get closer. you see that this large shape is made of individual massive coral heads and branching colonies. Move closer still, and you see that each colony is itself a complex, branching structure. Closer yet, and the very surface of the coral is a repeating pattern of individual polyps, each a tiny version of the larger whole. This infinite complexity is not just beautiful, it is the source of the reef's strength. This fractal branching creates the maximum possible surface area for feeding and sunlight, and it provides an almost limitless number of ecological niches, with hiding places for creatures of every size, from a large grouper down to a microscopic shrimp. Corals have a simple, primitive nervous system known as a nerve net, but they do not have a centralized brain. It is difficult to imagine how a creature that builds structures the size of mountains can operate without any central command. The coral colony, which is made of thousands of genetically identical polyps, functions as a collective consciousness, coordinated by a simple web of nerve cells. This nerve net spreads throughout the entire colony, connecting all the individual polyps, allowing them to communicate in a basic way. If one polyp is touched or senses a predator, it can retract for safety, and it sends a slow wave of neurological signals to its neighbors, causing a chain reaction of retraction that can spread across the entire coral head. This decentralized system allows the colony to react to its environment as a single unified organism, sensing the direction of the current to feed or detecting the shadow of a predator. It is a shared, communal intelligence, a city that thinks not with one mind, but with a million tiny connected whispers. Many species of coral are fluorescent, glowing with vivid, psychedelic colors when exposed to ultraviolet or blue light. If you were to visit a coral reef at night with a special blue light torch, the reef would transform into an otherworldly neon landscape. Corals that appear a simple brown or green in daylight will suddenly blaze with brilliant reds, electric greens, and fiery oranges. This glowing light is fluorescence. The coral possesses special proteins in its tissues that absorb the high-energy blue light and re-emit it as a lower-energy light of a different color. Scientists are still exploring the exact purpose of this dazzling display, but it seems to serve several functions. In deeper water, it may convert the only available blue light into colors that their symbiotic algae can use for photosynthesis. In shallow water, it may act as a powerful sunscreen, shielding the algae from the intense, damaging ultraviolet rays of the tropical sun. This living light is the coral's own private magic, a hidden beauty reserved for the light spectrums that we cannot normally see. The crown-of-thorn starfish, despite its destructive reputation, has a powerful natural predator. A large sea snail called the giant triton, the ocean, in its wisdom, always seeks balance. And for the formidable, coral-eating crown-of-thorn starfish, there is a specialized hunter. The giant triton is one of the largest and most magnificent snails in the sea, growing a beautiful spiraled shell that can reach up to 2 feet or over half a meter in length. This snail is not a gentle grazer. It is an active and relentless predator. It moves across the reef using its keen sense of smell, hunting for the chemical trail of the starfish. When it finds one, it seizes the spiny starfish with its strong muscular foot, uses its sharp, file-like tongue, or radula, to pierce the starfish's tough skin, and injects a paralyzing venom. It then slowly consumes its prey. These giant snails are a crucial part of the reef's immune system, but because their shells are so prized by collectors, their populations have dwindled, weakening the reef's natural defense against the starfish outbreaks. Sponges, which often grow alongside corals, are essential to the reef's nutrient cycle, acting as the lungs of the ecosystem. While the corals are the builders, the humble sponges are the reef's master janitors and recyclers. A sponge is a simple, porous animal that feeds by filtering enormous volumes of water, far more relative to its size than any other creature on the reef. A single sponge can filter thousands of liters or thousands of gallons of water every day. As they draw water in through their tiny pores, they consume microscopic bacteria, plankton, and tiny particles of organic waste. This process is a vital cleaning service, keeping the water clear and healthy for the corals. But the sponge's most magical role is what scientists call the sponge loop. Sponges are able to consume dissolved organic carbon, a form of nutrient that is unusable by most other reef inhabitants, and transform it into new living sponge cells. When these cells are shed, they become a delicious, nutritious food source for snails and crabs, effectively re-injecting lost energy back into the reef's food web. The first coral reefs appeared on Earth nearly 500 million years ago, long before the first dinosaurs roamed the land. When we look at a reef, we are seeing a truly ancient form of life, an ecosystem that has perfected the art of community building over vast geological epochs. The earliest coral-like reefs were built by creatures called tabulate and rugose corals, which thrived during the Paleozoic era. These ancient architects were completely different from the corals we know today, but they filled the same role, building massive stony structures in the planet's warm, shallow seas. These early reefs were pioneers, the first complex, three-dimensional habitats on the planet, and they witnessed the evolution of the first fish. They have endured through immense changes, surviving multiple mass extinction events that wiped out most other life on Earth. The corals of today, the scleractinian corals, only rose to prominence after the Great Permian extinction. The reef is therefore not just a place, but a legacy, a living echo of a 500 million year old memory, a form of life that the Earth has never been willing to forget. The relationship between the damselfish and its farm of algae is a rare example of agriculture in the animal kingdom. While the parrotfish is a nomadic grazer, the small territorial damselfish is a meticulous farmer. A single damselfish will stake out a small patch of the reef, perhaps on a dead coral branch, and claim it as its own. It will then cultivate a dense, private garden of its favorite algae within this territory. The fish is a tireless gardener, actively weeding its plot by pulling out any undesirable algae species to ensure its preferred crop can flourish. It will also fiercely defend its farm from any other creature that tries to graze on it, aggressively chasing away even fish that are many times its size, including parrotfish and surgeonfish. This small, determined creature has domesticated its food source, a perfect miniature farm that provides it with a constant, reliable supply of food. This behavior transforms a small patch of the reef's stony landscape into a private, well-tended garden, a small pocket of order created by one of the reef's most industrious residents. Some corals, in order to survive in murky, sediment-rich water, have learned to actively clean themselves. Corals need clean water and sunlight, but in coastal areas near river mouths, the water is often cloudy with suspended sediment. This sediment can be lethal, as it buries the polyps and blocks the sun. To survive in these challenging conditions, some corals have evolved a remarkable housekeeping ability. They can use the tiny hairs on their surface, the cilia, to create a current that slowly sweeps fine particles away. For larger debris, the coral can excrete a thick layer of mucus, a sticky net that traps the sediment. The coral then sheds this mucus coating, sloughing off the dirt and revealing its clean tissue underneath. Some species, like the mushroom coral, can even inflate their bodies with water to puff themselves up, causing the sediment to roll right off their dome surface. This is the reef's quiet determination, its refusal to be buried, a slow, patient act of cleansing that allows life to persist even when the water grows dark. The Great Barrier Reef is so large that it has its own post office, located on a small floating pontoon. In the midst of the vast aquatic wilderness of the Great Barrier Reef, 100 kilometers or about 60 miles offshore from the mainland, human life has found a small foothold. On a large, permanently moored pontoon known as the Reef World Platform, which serves as a base for divers and tourists, there is an official, functioning post office. Visitors can write a postcard from this unique location, have it stamped with a special postmark, and send it anywhere in the world. This small box, floating above the world's largest living structure, is a charming and whimsical intersection of two vastly different worlds. It is a symbol of how deeply this natural wonder has captured the human imagination, a place so significant that we have felt the need to connect it to our own global network, sending letters from the heart of the ocean, delivered from a small metal island adrift in a sea of coral. The sound of motorboats can interfere with the ability of young fish to find a suitable home on the reef. For a tiny larval fish, born in the open ocean, the journey home to the reef is the most critical challenge of its life. It navigates this vast blue emptiness, not just by sight or smell, but by listening. It is tuned to the specific sounds of a healthy reef, the crackle of shrimp and the crunch of parrotfish, which act as a homing beacon. However, the modern ocean is filled with new, unfamiliar sounds, particularly the low-frequency roar of boat engines. This man-related noise can travel long distances underwater and can completely mask the subtle, natural sounds of the reef. Young fish, swimming through this acoustic fog, become confused and disoriented. Studies have shown they are less able to find the reef, and those that do are slower to hide from predators, as the noise impairs their ability to react. This is the ocean's version of light pollution, an invisible disruption that drowns out the quiet voices of the ecosystem, making the journey home for the reef's smallest children an even more perilous quest. A super coral is a coral that has shown an extraordinary ability to survive in water that is unusually warm or acidic. As the ocean environment changes, the reef is in a desperate race against time, and in this race, some individuals have shown remarkable strength. These are the supercorals. They are not a distinct species, but rather individuals or colonies that have, through genetic luck or rapid adaptation, developed a high tolerance for the stresses that kill their neighbors. Scientists are now actively searching for these resilient corals, studying their genes and their symbiotic algae to understand the secret to their toughness. They are found in naturally extreme environments, such as shallow lagoons that regularly overheat, or near volcanic vents with more acidic water. These survivors are the great hope for the future of reefs. They are living laboratories of resilience, and conservationists are now working to cultivate and propagate these strong corals, hoping to one day reseed damaged areas with the tough, hopeful offspring of these remarkable champions of survival. The mantis shrimp, a common reef inhabitant, possesses one of the most complex visual systems in the entire animal kingdom. The coral reef is a world defined by color and light, a visual symphony of breathtaking complexity, but we are only able to perceive a fraction of its true appearance. Hidden within the reef's crevices is a small, armored predator, the mantis shrimp, which experiences this world in a way we can barely comprehend, while human eyes are trichromatic, meaning we have 3 types of color-receptive cone cells to see reds, greens, and blues. The mantis shrimp possesses between 12 and 16. This means they see a vast, hyperspectral world, perceiving a rainbow of colors that are utterly unimaginable to the human mind, including many different wavelengths of ultraviolet light. But their visual prowess does not end there. They can also perceive and differentiate between various forms of polarized light. This ability is used as a secret, high-speed communication channel, allowing them to flash patterns on their own bodies that are invisible to predators but crystal clear to a potential mate. They see a version of the reef that is painted in a million extra colors, a landscape filled with hidden messages written in the language of light, a profound reminder that our own perception of reality is just one limited slice of the full, vibrant truth. Many species of coral-dwelling fish, like the famous clownfish, have the ability to change their sex, a strategy that ensures the survival of the group. The reef is a complex and often crowded society, but for some species, life is lived in small, isolated family groups, such as the clownfish that spend their entire lives within the protective tentacles of a single anemone. In such a small, closed community, finding a new mate if one is lost can be an impossible challenge. To solve this, these fish have evolved a remarkable fluid identity known as sequential hermaphroditism. A clownfish group is a strict hierarchy. It is led by one large dominant female, with one smaller active breeding male, and several even smaller non-breeding juvenile males. If the large female dies, the social order does not collapse. Instead, the breeding male's body will physically transform. He will grow larger and over a period of weeks will become the new dominant breeding female of the group. The largest of the juvenile males will then mature and take his place as the new breeding male. This is nature's profound solution for continuity, a form of social and biological transformation that bends to the needs of the community, ensuring that life's lineage is never broken by the loss of a single individual. When threatened, the humble sea cucumber can expel its own internal organs out onto the seafloor as a startling defense mechanism. The sandy floor of the reef is home to many slow-moving, soft-bodied creatures like the sea cucumber, which appear to have no defenses at all. Lacking speed, armor, or sharp spines, they have instead evolved one of the most dramatic and sacrificial strategies in the animal kingdom. When a predator, such as a large fish or crab, attacks, the sea cucumber will violently contract its body wall and undergo a process called evisceration. It will forcibly eject a long, tangled mass of its internal organs, often its sticky respiratory trees and parts of its digestive tract. Out through its anus, these organs, often toxic, can entangle and confuse the predator, which may be satisfied with this meal, allowing the sea cucumber itself to slowly crawl away to safety. This act appears to be a final, fatal sacrifice, a complete self-destruction. But this is not the end. The sea cucumber possesses an almost magical power of regeneration, and over the next few weeks, it will calmly and completely regrow its entire lost set of internal organs, a living testament to the idea that sometimes survival requires a profound act of letting go, a complete surrender in order to become whole again. A coral atoll, the beautiful ring-shaped island enclosing a lagoon, is actually the final stage in the life of a massive sunken volcano. We see these perfect circles of white sand and green palms in the middle of the vast, empty ocean, and they appear as if they rose from the deep built by the corals alone. But their story begins millions of years ago, as told by Charles Darwin, with the fiery birth of a new volcanic island. As this mountain rises from the seafloor, a young, fringing coral reef begins to grow in the shallow water around its new shoreline. For thousands of years, the island stands tall, but eventually, the dormant volcano begins to slowly sink under its own immense weight, a process called subsidence. The corals, which must stay near the sunlit surface, grow continuously upwards, building their fortress higher and higher. Keeping perfect pace with the sinking land, the island itself shrinks, leaving a wide, deep lagoon separating the land from the growing barrier reef. Finally, the volcanic peak sinks entirely beneath the waves, disappearing forever into the deep, leaving only the living ring of coral at the surface, which has now become an atoll, its central lagoon a final blue mirror. Remembering the mountaintop that once was, the atoll is therefore a living monument, a beautiful sunlit wreath laid upon the grave of a forgotten mountain, a perfect circle of life built upon the foundations of geologic time. The venom of the cone snail, one of the reef's most unassuming predators, contains compounds that have led to a powerful new class of painkillers. The reef is a silent, chemical battlefield, and survival often depends on potent, invisible weapons. The beautiful, geometrically patterned cone snail is a slow-moving predator, yet it hunts fast-moving fish. It cannot chase its prey, so it has evolved a biological harpoon. The snail extends a long, tube-like proboscis and fires a single, barbed, hollow tooth into its victim, injecting a complex cocktail of hundreds of different venoms, called conotoxins. This venom is so powerful it can paralyze a fish almost instantly. Scientists, in studying this remarkable toxin, discovered that certain peptides within it are incredibly effective at blocking specific pain pathways in mammals, including humans, in a way that is completely different from traditional medicines. One of these compounds is now the basis for a potent, non-addictive pain medication that is many times more powerful than morphine, used for patients with severe chronic suffering. This quiet, deadly hunter, in its patient quest for survival, has inadvertently perfected a molecule that offers profound relief, a hidden gift from the reef's ancient chemical library. Large, predatory fish, like sharks and groupers, will patiently line up at specific cleaning stations on the reef to be serviced by tiny cleaner wrasse. In the complex, bustling city of the reef, there are designated locations, often a prominent coral head or rocky outcrop, that serve as a communal spa and health clinic. These stations are run by the tiny, brightly colored cleaner wrasse, a fish that is perhaps only a few inches or several centimeters long. The true magic of this place is the truce it commands. Large, formidable predators, which would normally eat a small fish like the wrasse without a second thought, arrive at the station and adopt a calm, unthreatening posture. They will signal their intent by opening their mouths wide and flaring their gills. The tiny wrasse, recognizing this universal sign for service, will bravely swim all over the predator's body and even deep inside its mouth and gills, meticulously picking off and eating parasites, dead skin, and bacteria. This is a vital healthcare service that keeps the entire community healthy, and in return, the wrasse receives a constant, reliable source of food. This is a place of profound interspecies trust, a sanctuary where the normal, hard rules of predator and prey are suspended, where even the ocean's most fearsome hunters must pause, become vulnerable, and accept the gentle care of a creature a fraction of their size. Corals can communicate with each other using chemical signals, but this communication is entirely dependent on the flow of water. A coral reef may appear to be a collection of silent, isolated individuals, each stony colony locked in its own quiet existence. But the reef is a dense city of stationary animals, and they are all connected by the very medium that surrounds them. The water's current is the reef's circulatory system, its shared atmosphere, and its primary information network. When a coral is damaged, perhaps by the bite of a parrotfish, it releases a chemical alarm compound into the water. As these invisible compounds drift downstream on the current, they are detected by other corals, which receive the message of a nearby threat. These neighboring corals can then respond, perhaps by retracting their polyps for safety, or by beginning to produce their own defensive chemicals before the danger even arrives. This same watery internet is what allows the reef to synchronize its mass spawning, as the release of reproductive cells by one colony sends a chemical cue to its neighbors that the time is right. The reef is not a silent place, but a single sprawling organism, connected by the invisible flowing language of the water, a constant shared stream of consciousness that whispers of danger, of opportunity, and of the turning of the seasons. While corals are the builders of the reef, an entire community of other organisms, known as bioeroders, spends its life slowly breaking the reef down. We celebrate the reef as a marvel of construction, a constant, patient process of building upwards, of life-conquering stone. But like any great ancient city, the reef is also a place of constant demolition and recycling, a vital process known as bioerosion. An entire community of unbuilders works tirelessly to disassemble the reef's stony foundations. This includes the large parrotfish, which grind the surface to powder, and the spiny sea urchins, which scrape algae with powerful, self-sharpening teeth, gouging the rock beneath. But the most significant architects of this change are often hidden. Certain species of sponges, like Cleona, chemically bore their way into the coral skeleton, creating a network of tunnels and cavities from the inside out. Weakening the structure, marine worms and bivalves also drill deep into the stone, seeking a protected home. This constant scraping, grinding, and boring is not destruction. It is a necessary and creative disassembly. These bioeroders are the reef sculptors, the recyclers who create the sand, the sediment, and the countless complex hiding places that the reef's other residents depend on, ensuring the reef is not a static monument, but a dynamic, ever-changing, and breathing landscape. The modern Great Barrier Reef, despite its ancient appearance, is actually quite young, with most of its current structure being less than 10,000 years old. The life of coral is ancient, stretching back hundreds of millions of years, which gives the impression that the Great Barrier Reef itself is an eternal, unchanging monolith. But the structure we see today is a relatively recent creation, a story of profound environmental change. The planet's ice ages caused sea levels to rise and fall dramatically. During the peak of the last ice age, around 20,000 years ago, so much of the Earth's water was locked up in massive glaciers that the sea level was over 120 meters, or nearly 400 feet, lower than it is today. The entire continental shelf where the reef now sits was exposed as dry land, a series of coastal plains and low hills. The reef we see today only began to grow around 10,000 years ago, as the ice melted and the seas rose, slowly drowning that ancient landscape. The corals recolonized the submerged hills, which now form the foundations of the current reefs, patiently growing upwards as the water rose. The reef is a story of death and rebirth, a living, vibrant city built directly on the foundations of an older, drowned world, a testament to the planet's powerful, cyclical breathing of ice and water. The world's heaviest bony fish, the massive and gentle mola mola, is a frequent visitor to coral reefs, seeking out their cleaning stations. The deep, open ocean is a realm of giants, and one of its strangest and largest inhabitants is the ocean sunfish, or mola mola. This is a bizarre and enormous creature, weighing over 2,000 kilograms or 5,000 pounds, which appears as if it is just a giant, swimming head with two large fins, its body seeming to be cut short. These gentle giants spend most of their lives in the lonely darkness of the deep, feeding on jellyfish. However, their slow-moving life and leathery skin make them a perfect host for a huge number of skin parasites, sometimes carrying over 40 different species to find relief. The mola mola will travel from the open ocean to the coastal coral reefs, where it visits the same cleaning stations used by the small, resident fish. It will bask on its side near the surface, a huge, pale disc, and allow the tiny cleaner wrasse to swarm its body, picking it clean in a frenzy of activity. This great, weary traveler from the deep must return to the reef's busy community for healing, a testament to the reef's role as a vital sanctuary and hospital for all, from the smallest resident to the largest visitor of the open sea. The tiny, beautiful blue-ringed octopus, often found in reef tide pools, carries a venom so potent it can be lethal to a human, and there is no antivenom. The coral reef is a world of vibrant colors, and these colors often serve as a warning. The blue-ringed octopus, sometimes no larger than a golf ball, is perhaps the most dramatic example. While resting, it is a drab, yellowish-brown, blending perfectly with the sand and rubble. But when it is threatened, it instantly transforms, its skin flashing a pattern of 50 to 60 iridescent electric blue rings, a stunning and unmistakable signal. This is its final stark warning. It does not have fangs, but a small, sharp beak, and its bite delivers a powerful neurotoxin called tetrodotoxin, the same deadly toxin found in pufferfish. This toxin works by completely blocking the body's nerve signals, leading to muscle paralysis. A person who is bitten may remain fully conscious, but find themselves unable to move, speak, or, most critically, breathe. There is no antivenom, and the only treatment is to be put on a mechanical ventilator, to have a machine breathe for the body, until the toxin slowly and naturally wears off, a process that can take many hours. This small, jewel-like creature is a vessel of profound power, its beauty a final silent plea for respect. Tiny trapezoid crabs live their entire lives deep within the branches of branching corals, acting as a personal bodyguard for their coral home. The dense, forest-like branches of a staghorn or acropora coral are a perfect, three-dimensional fortress, an apartment complex for a multitude of tiny creatures. Among the most loyal of these residents are the small trapezoid crabs. A pair, often a male and female, will settle into a coral head when they are young, and, in many cases, never leave it for the rest of their lives. They are completely dependent on their living home, which provides them with a safe, protected space and a constant source of food, as the coral exudes a fatty, nutritious mucus that the crabs eat. In return, these crabs are fierce, miniature guardians. If a predator, such as the coral-eating crown-of-thorns starfish, tries to climb onto the coral, the tiny crabs will swarm out from the branches, brandishing their small claws and pinching at the starfish's soft, vulnerable tube feet. annoying and repelling the predator until it is forced to retreat. This is a story of miniature, unseen loyalty, where the huge, stony coral is protected not by its own size, but by the collective courage of its smallest, most faithful residents. The largest of all parrotfish, the giant humphead parrotfish, is so large it can ram its head into corals to break them apart before eating them. We are familiar with the smaller parrotfish that gently scrape the reef surface, but there is a titan in this family, a true giant of the reef. The humphead parrotfish can grow to be 1.5 meters, or nearly 5 feet, long and weigh over 75 kilograms, or 165 pounds. It is instantly recognizable by the large, bulbous protrusion on its forehead, a thickened part of its skull that it uses as a living battering ram. These large fish often travel in schools, descending on a section of reef like a herd of grazers. They will use their powerful heads to physically smash into the coral, breaking off large chunks of the stony structure. They then use their powerful, fused beak-like teeth to grind up the coral rock and skeleton, digesting the algae and polyps living within a single humphead parrotfish. In its relentless search for food, can consume over 5 tons of reef carbonate in a single year. This creature is a powerful, primal force of nature, one of the primary agents of bioerosion, and a grand sculptor of the reef's landscape, a living hammer that shatters the old to make way for the new. The Australian box jellyfish, one of the most venomous animals on Earth, breeds in coastal mangrove estuaries, and its adult form often hunts near coral reefs. The calm, warm, and inviting waters of the tropical reef can sometimes hide a danger that is almost invisible. The box jellyfish, with its pale blue, transparent bell and long, trailing tentacles, is one such phantom. This creature, Chironex fleckeri, is infamous for its extraordinarily potent sting. It has a cube-shaped bell and can trail up to 60 delicate tentacles, each one stretching as long as 3 meters, or about 10 feet. These tentacles are covered in millions of microscopic stinging cells that, upon the slightest touch, inject a powerful venom that attacks the heart, the nervous system, and the skin, causing excruciating pain and, in severe cases, death within minutes. While these jellyfish do not live on the reef itself, their life cycle brings them into the same coastal waters as they breed in the murky mangrove rivers and then move out to the clear shallows to hunt for fish and prawns. This beautiful, glassy creature is a whisper of danger, a reminder that the ocean's beauty is often wild and untamed, a delicate, translucent form that carries within it the very essence of nature's power. The sargassum fish is a master of camouflage, perfectly mimicking the appearance of the floating seaweed that sometimes drifts over coral reefs. In the open ocean, great golden brown mats of sargassum seaweed drift on the currents, forming a unique, wandering ecosystem, a golden, floating reef. Sometimes, these large mats are blown by wind and current into coastal waters, where they drift over the coral reefs below. Living within this tangled, floating world is the sargassum fish, a type of frogfish that is a true master of disguise. Its body is a mottled yellow and brown, covered in strange, fleshy appendages, fins, and flaps of skin that look exactly like the leaves, stems, and air bladders of the surrounding seaweed. It is a lion-weight predator, holding perfectly still within its camouflage. Its first dorsal fin has evolved into a long fishing rod-like appendage called an elysium, which has a fleshy lure, or esker, on the end. It dangles this lure to attract small fish and shrimp, and when they come close, The frogfish opens its massive mouth with one of the fastest movements in the animal kingdom. Sucking its prey in this creature is a living illusion, a patient hunter that has blurred the line between itself and its wandering golden home. In some parts of the world, resilient coral reefs have been found growing in the cold, dark, and acidic waters of high-latitude fjords. Our image of coral is inextricably linked to warm, clear, tropical seas, bathed in bright sunlight. The idea of a coral reef existing in a cold, deep, northern fjord seems like an impossibility. Yet, scientists have discovered vast, thriving, and ancient reefs of the deep-water coral Lophilia pertusa inside the fjords of countries like Norway. These reefs are existing in a collection of conditions that should be lethal to coral. The water is perpetually cold, often only 6 to 8 degrees Celsius, or about 43 to 46 degrees Fahrenheit. It is also naturally more acidic than the open ocean, due to the heavy freshwater runoff from the surrounding mountains, which should make it incredibly difficult for the corals to build their calcium carbonate skeletons. And yet, these pale white reefs are ancient, some thousands of years old, building massive structures in the total darkness that are teeming with life, serving as vital hotspots of biodiversity for deep-sea fish and invertebrates. These are the hidden reefs of the North, a silent, thriving kingdom that reminds us that life's desire to build is more stubborn and powerful than we can possibly imagine. The epaulet shark, a small shark that lives on the Great Barrier Reef, has evolved the ability to walk on land when it gets trapped in tide pools. The reef is a world of constant change, and this is especially true on the shallow reef flats. When the tide goes out, it can leave behind a maze of shallow, isolated pools, stranding the marine life within. For most fish, this situation is a death sentence, as the sun rapidly heats the water and the oxygen levels plummet. The small epaulet shark, however, is perfectly adapted to this challenge. It can intentionally slow its breathing and heart rate, allowing it to survive for hours in water with almost no oxygen. More remarkably, it has evolved to use its pectoral and pelvic fins as stout, muscular, leg-like limbs. It can physically pull itself up and out of the water, walking or wiggling its body across exposed stretches of dry coral or rock, moving from one tide pool to another, deeper one. This small, determined shark is a living portrait of evolution in action, a creature of the sea that has relearned the ancient, necessary movement of land, a pioneer that refuses to be trapped by the ocean's changing boundaries. Moray eels and large grouper fish have been observed actively hunting together, using two different strategies to trap their prey. In the ocean, most predators are solitary hunters, relying on their own strength and skill. But on the reef, two of the top predators from entirely different families have formed a sophisticated and conscious hunting alliance. The grouper is a large, powerful fish that hunts in the open water above the coral. The moray eel is a long, slender, and flexible hunter that snakes through the narrow, twisting crevices inside the reef. Their prey, small fish, have a simple defense. They hide from the grouper by darting into the reef, and they hide from the eel by darting out into the open. But when the two hunt together, this defense fails. The grouper will chase a fish into a hole and then signal to the eel, often with a specific head shake, indicating which crevice the prey has entered. The eel will then swim into that crevice, flushing the prey out from its hiding place, sending it directly into the open, waiting mouth of the grouper. This is a complex cross-species collaboration, a silent, predatory language spoken between two different minds, united in a perfect lethal partnership. The smell of a healthy coral reef, a sulfur compound called dimethyl sulfide, is a vital chemical cue that guides seabirds and other marine life. If you have ever been near a healthy, vibrant tropical reef, you may have noticed a distinct, sulfurous ocean scent on the air. This is not the smell of decay, it is the smell of life, a chemical perfume breathed out by the reef itself. The microscopic symbiotic algae living within the coral tissues produce a chemical called DMSP. When this compound is released and breaks down in the water, it creates dimethyl sulfide, or DMS, a volatile gas that rises into the atmosphere. This scent is a powerful airborne beacon. Large, ocean-roaming seabirds, like albatrosses and petrels, have a keen sense of smell and use this scent to find the highly productive waters of the reef from many miles or kilometers away, knowing it is a rich feeding ground. It is also believed that other large marine animals, like whale sharks and sea turtles, may follow the same chemical trail in the water to navigate to the reef. The reef announces its health to the world, a guiding aromatic map for the great travelers of the sea and sky. Coral reefs in the Red Sea are exceptionally resilient to high water temperatures, making them a unique natural laboratory for studying coral survival. In a world where rising ocean temperatures are the primary threat to coral health, the reefs of the Red Sea stand apart as remarkable oases of endurance. This long, narrow basin is one of the warmest and saltiest seas on Earth. The corals here, particularly in the northern sections like the Gulf of Aqaba, have adapted to a thermal environment that is already far hotter than the bleaching thresholds for corals in the Pacific or Caribbean. They routinely thrive in summer water temperatures that reach 32 degrees Celsius, or nearly 90 degrees Fahrenheit, conditions that would cause catastrophic bleaching almost anywhere else. Scientists believe this incredible resilience was forged by the sea's own geological history. As corals recolonized the Red Sea after the last ice age, they had to pass through the extremely hot and salty waters of the southern entrance, a harsh environmental filter that selected only the most heat-tolerant individuals. These corals now carry this thermal-resistant legacy in their genes, offering a profound, living blueprint of what a future, warmer water coral reef might look like. The beautiful, feathery sea fans that adorn the reef are not plants, but a type of soft coral called a gorgonian. As we drift through the reef's gardens, our eyes are drawn to the delicate, intricate fans that stand perpendicular to the current, some as large as a person, gently swaying like purple and orange lace. It is easy to mistake them for a type of exotic seaweed, a plant anchored to the stone. But these are animals, a colony of tiny polyps just like their hard-bodied cousins, but with a crucial difference. Instead of building a rigid calcium carbonate skeleton, they secrete a flexible, protein-based internal skeleton called gorgonin, which is much like our own fingernails. This gives them their toughness and flexibility, allowing them to bend and sway without breaking. Their distinct, flattened, fan-like shape is a masterpiece of natural engineering. By orienting themselves perfectly against the prevailing current, they create a living net, maximizing the surface area for their thousands of tiny polyps to extend their tentacles and filter feed on the microscopic plankton drifting by. They are the reef's living filters, patient, beautiful sieves that have learned to harvest the ocean's bounty by yielding to its flow. The tiny, seemingly insignificant Christmas tree worm bores into a living coral head and spends its entire life in that one spot. Peeking out from the surface of many large boulder corals are pairs of small, vibrant, spiral-shaped plumes that look like tiny, colourful fir trees, often in bright shades of yellow, blue or red. These are the Christmas tree worms, and they are far more than just surface decorations. Each worm, when it is young, has burrowed deep into the coral's living skeleton, creating a permanent, stony tube to live in. The beautiful, spiraling plumes we see are actually the worm's highly modified, feathery gills, which it extends into the water to perform two tasks at once. They breathe for the worm, and they trap microscopic food particles, which are then passed down a groove to the worm's hidden mouth. These worms are incredibly shy. They are highly sensitive to changes in light or pressure, and if a shadow passes over, they will retract their colourful trees into their stony burrow with lightning speed, disappearing in a flash. The coral provides a safe, permanent fortress, and the worm, in return, adds another layer of vibrant, living beauty to the coral's stony surface, a small, shy guest that becomes a permanent jewel in the home it has chosen. The relationship between corals and certain species of seaweed is not always competitive. Some corals actually farm algae on their own skeletons. We often view the relationship between coral and algae as a war for space, a battle between the stony builders and the fleshy, fast-growing plants. But nature's relationships are rarely so simple. Scientists have discovered that some species of branching coral, like the finger-like Porite cylindrica, actively cultivate and manage small, discrete patches of filamentous algae, or turf algae, deep within their own branches. This seems counterintuitive, as the algae could smother the coral. However, the coral carefully controls the growth of this algae, keeping it in check, and in return, the algae provides a crucial service. The algae fix nitrogen from the seawater, converting it into a form that the coral can use as a vital nutrient, a fertilizer for its own internal zooxanthellae. In this arrangement, the coral is a farmer, giving the algae a safe, protected place to live, and in return, the algae provides the coral with a vital nutrient that is scarce in the surrounding water. This is a form of partnership that transforms a potential competitor into a cultivated domestic crop. The snapping shrimp, the tiny creature responsible for the reef's crackling sound, creates its snap by generating a bubble that is as hot as the surface of the sun. The constant, sizzling, static-like sound of a healthy reef is the signature of the tiny pistol shrimp. This sound is not made by its claws clicking together, but by a feat of extreme physics. The shrimp has one oversized, specialized claw that has a plunger and a corresponding socket. When the shrimp cocks and snaps this claw shut, the plunger moves so fast that it shoots a high-speed jet of water, creating a tiny air bubble in its wake. This bubble is no ordinary bubble. It is a phenomenon known as a cavitation bubble. The pressure in the bubble is so low that the water around it instantly vaporizes, but this state lasts for only a microsecond. The bubble then violently collapses in on itself, and for a fleeting, microscopic moment, the temperature inside that collapsing bubble reaches over 4,700 degrees Celsius, or about 8,500 degrees Fahrenheit, a temperature comparable to the sun's surface. This collapse creates a shockwave and a bright flash of light, and it is the shockwave, not the snap, that we hear as the pop. This tiny creature, hidden in a crevice, wields the power of a star to stun its prey, a microscopic explosion that, when multiplied by thousands, becomes the reef's living pulse. Some species of parrotfish sleep at night by enveloping themselves in a transparent sleeping bag made of their own mucus. The reef is a dangerous place for a fish, even at night, as predators like moray eels are active hunters, and many creatures, like the parasitic isopods, seek out resting fish. The parrotfish has evolved a remarkable and slightly bizarre form of protection to ensure a safe night's rest. As dusk settles, the fish will find a safe crevice in the reef and begin to secrete a thick, clear mucus from specialized glands in its gills. It takes the fish about an hour to completely envelop its entire body in this see-through, gelatinous cocoon. This sleeping bag serves two critical purposes. First, it masks the fish's scent, making it effectively invisible to nocturnal predators like eels that hunt primarily by smell. Second, it acts as a physical barrier, a bug net that prevents small, blood-sucking parasites from attaching to the fish's skin and gills while it sleeps. In the morning, the fish simply bursts out of its cocoon, leaving the used pajamas behind, and begins its day of grazing, fully rested and protected by its own strange, self-made blanket. The seafloor around a coral reef is often covered in strange, circular patterns, known as fairy rings, which are created by a specific species of stingray when seen from above. The sandy halos surrounding coral bommies often contain perfect large circles, as if a compass had been drawn in the sand. These are not geological formations, but the feeding grounds of the whiptail stingray. This ray feeds on small invertebrates, like worms and crustaceans, that are buried deep within the sand. To find them, the ray settles on the bottom and begins to pivot its body in a perfect circle, using its powerful wings to rhythmically flap and excavate the sand beneath it, digging a deep circular trench. It uses its electroreceptors to detect the buried prey, which are exposed by the digging. The ray will create one of these feeding pits, consume the prey, and then move a few feet, or about a meter, away and repeat the process, creating a series of overlapping rings. This behavior is a form of systematic foraging, an organized geometric tilling of the seafloor that leaves behind a beautiful, mysterious pattern, the signature of a hidden hunter's patient search for food. The mimic octopus, a reef dweller, is not limited to just changing its color. It can actively change its body shape and behavior to impersonate other, more dangerous animals. The coral reef is the pinnacle of the art of camouflage and illusion. But one creature has taken this art to an unparalleled level. The mimic octopus, found in the sandy, silty bottoms near Indonesian reefs, is a true shapeshifter. While all octopuses can change their skin color and texture, the mimic octopus goes further, altering its entire posture and, critically, its behavior. If it is being threatened by a territorial damselfish, it will tuck in 6 of its arms, change its colors to black and yellow, and swim in the open, perfectly impersonating a venomous sea snake, which is a predator of the damselfish. To move across the open sand, it will pull its arms together, flatten its body, and glide along the bottom with a rippling motion, perfectly mimicking a flatfish. It has also been observed impersonating the venomous spines of a lionfish and the posture of a sea anemone. This octopus is a living library of identities, a master illusionist that survives not by hiding, but by becoming the very thing its enemies have learned to fear. The pygmy seahorse is so small and so perfectly camouflaged that the species was undiscovered until the 1960s, when a piece of sea fan coral it lives on was collected for a museum. The vast, intricate branches of a Gorgonian sea fan are a world unto themselves. and hidden within this delicate purple forest is one of the smallest and most elusive fish in the ocean. The pygmy seahorse, specifically Bargibant's pygmy seahorse, grows to be less than 2 centimeters or under an inch long. Its entire life is spent clinging to the branches of its specific host sea fan. Its camouflage is not just mimicry, it is perfection. The seahorse's body is the exact same color as the sea fan's branches, and its skin is covered in small bulbous tubercles that are identical in shape and color to the polyps of the coral it lives on. This camouflage is so complete that the fish is virtually invisible, even to a trained eye, unless it moves. The species was only formally described in 1969, when a scientist was examining a collected sea fan in a laboratory and happened to notice 2 of these tiny, impossible creatures clinging to its branches. This tiny, perfect jewel of the reef is a reminder of the ocean's undiscovered secrets, a life that has learned to survive by becoming an inseparable part of its home. Some reefs are built not by corals, but by massive, ancient colonies of shelled worms. When we think of a reef, we instinctively picture the calcium carbonate skeletons of stony corals, but in some parts of the world, particularly in the cooler waters around places like Bermuda or the Mediterranean, the primary architects are entirely different. Here, you can find large reef structures, some spanning many acres, built entirely by the patient, collective work of tiny tube-dwelling worms, specifically the serpulid worms. These worms, much like corals, extract calcium carbonate from the seawater to build hard, protective tubes around their soft bodies. They grow in dense, tangled aggregations, with new generations of worms building their tubes on top of the old, empty ones. Over many hundreds or thousands of years, this slow, steady accumulation of tiny, stony tubes fuses together to create a massive, porous, and complex reef structure. These worm reefs, or vermeted reefs, function just like coral reefs, providing a vital, 3-dimensional habitat for fish and invertebrates, a testament to nature's diverse and inventive ways of building cities from the sea. The bright colors of many reef fish, like the mandarin fish, are not created by pigments, but by the physical structure of their skin cells. The reef is a kaleidoscope, but some of its most spectacular colors are a form of physical magic, an illusion of light itself. The mandarin fish, a small, shy creature that emerges at dusk, is covered in a breathtaking, psychedelic pattern of electric blue and bright orange swirls. These colors are not pigments, which are chemicals that absorb certain wavelengths of light. Instead, the mandarin fish has specialized skin cells called iridophores. These cells contain microscopic crystalline plates of guanine. When light strikes these plates, it is refracted and reflected in a very specific way, a phenomenon known as structural coloration. This physical interference with light waves cancels out all colors except for the brilliant, shimmering blue that we see, a blue that is purer and more intense than any pigment could produce. The orange, by contrast, is a true pigment. This fish has mastered 2 different forms of color, painting itself with both chemical paint and with captured structural light, a living jewel that bends the very physics of the visible world to create its beauty. The banded sea crate is a type of sea snake that must come to shore, often on coral islands, to lay its eggs and digest its food. The coral reef is a world poised between 2 realms, the land and the sea, and some of its inhabitants must navigate both. The banded sea crate is a beautiful, air-breathing reptile, a snake with a flattened, paddle-like tail, perfectly adapted for swimming. It is a specialized hunter on the reef, using its potent venom to hunt moray eels and other fish hidden deep within the coral crevices. But despite its aquatic life, it is not fully divorced from the land. Unlike true sea snakes, which give birth to live young in the water, the sea krait is oviparous, meaning it must lay its eggs. It must heave itself out of the ocean, often under the cover of night, and crawl awkwardly onto the rocky shores of coral cays and atolls to find a crevice to deposit its eggs. It will also rest on land to digest its large meals and shed its skin. This creature lives a dual existence, a serpent of two worlds, forever tied to the solid ground of the reef's islands, while drawing its living from the water that surrounds them. The largest bivalve in the world, the giant clam, lives on the reef and can weigh over 200 kilograms, or 550 pounds embedded in the reef. Like massive living sculptures are the giant clams. These are the titans of their kind, some growing to over 1.2 meters, or 4 feet, in length, and living for over 100 years. Their two huge fluted shells are often open, revealing a spectacularly colored fleshy mantle that shimmers in shades of electric blue, vibrant green, and intricate gold. This brilliant color serves the exact same purpose as it does in coral. The clam's mantle is a greenhouse, packed with the same symbiotic zooxanthellae algae. The clam positions its mantle to receive the maximum amount of sunlight, and the algae photosynthesize, providing the huge animal with a steady supply of food. The clam is, in effect, a self-contained solar-powered garden. It is so large and heavy that once it settles, it is a permanent resident of the reef, a patient, ancient being that simply rests, filters the water, and soaks in the sun. Its beautifully patterned mantle, a living testament to its silent partnership with the light. The green sea turtle, a common reef resident, has an incredible navigation ability, using the Earth's magnetic field to find its nesting beach. The coral reef serves as a vital feeding ground for the graceful green sea turtle, which grazes on the algae and seagrasses that grow in the reef's lagoon. But these turtles are also great oceanic voyagers, tied to an ancient, invisible map. A female turtle, when she is ready to lay her eggs, will embark on an epic migration, sometimes traveling over 2,600 kilometers, or more than 1,600 miles, across the open, featureless ocean to return to the exact same beach where she herself was born decades earlier. For a long time, how they achieved this pinpoint navigation was a profound mystery. Scientists now believe they are using the Earth's magnetic field as a natural compass. They can detect both the angle and the intensity of the magnetic field, which gives them a unique magnetic address for any spot on the globe. This allows them to sense their position and navigate with extraordinary precision, following an unseen planetary grid, a magnetic memory that guides them home across 1,000 miles of water. Some coral reefs, known as booming reefs, can be heard for several kilometers underwater, a sound produced by millions of fish communicating at once, while the crackle of shrimp is the reef's baseline sound. At certain times, a much deeper, louder, and more mysterious sound emerges. At dusk and dawn, during the spawning season for certain species of fish, the reef begins to boom. This is a deep, low-frequency, chorus-like sound that can be so intense it is audible to divers as a physical vibration in their chests. This sound is not from one large creature, but from the combined voices of millions of small fish, like damselfish and soldierfish, all vibrating their swim bladders at the same time. This is a communal social call, a synchronized signal used to coordinate the mass release of eggs and sperm. a call to aggregation. This booming is the reef's collective voice, a deep, resonant hum that announces the precise moment of spawning, a shared, rhythmic chant that ensures the next generation of the reef is born in perfect, harmonious unison. The electric ray, a relative of skates and sharks, can be found resting on the sandy bottoms of reefs, capable of producing a powerful, debilitating shock. Lurking on the sandy plains between coral heads, often completely buried with only its eyes protruding, is a master of bioelectricity. The electric ray, or torpedo ray, appears as a soft, fleshy, rounded disc, a seemingly harmless and slow-moving creature. But hidden within its wing-like pectoral fins are two large, kidney-shaped organs made of specialized, stacked muscle cells called electrocytes. These function as a living biological battery. When a prey item, like a fish, swims overhead, or if a predator threatens it, the ray can instantly discharge its stored power in a single, massive jolt, producing a shock of up to 220 volts. This is more than enough to instantly stun or kill its prey and deliver a painful, incapacitating warning to any creature that disturbs it. This silent, patient hunter does not need speed or venom. It has harnessed the very power of lightning, waiting in the sand with a quiet, charged potential. The filefish, a common reef fish, avoids predation by biting off and eating the polyps of a specific type of acrid-smelling soft coral, thereby making itself taste and smell terrible. In the eat or be eaten world of the reef, defense can take many forms, and one of the most clever is to become unpalatable. The filefish is a slow-moving, vulnerable fish, but it has a unique strategy. It actively seeks out and grazes on a particular type of soft coral that, to most other creatures, is noxious and repulsive. Filled with defensive chemical compounds, the filefish is one of the few creatures that can eat this coral. It then absorbs these unpleasant chemicals and sequesters them into its own skin and mucus. The result is that the filefish itself takes on the foul taste and smell of the coral it eats. A predator that tries to bite the filefish gets a mouthful of this terrible flavor and will quickly spit the fish out and learn to avoid it in the future. This is a form of chemical camouflage, a "you are what you eat" defense, where the fish has created a living, unappetizing shield from the stolen chemical weapons of its own food. The male seahorse is the only animal on the planet in which the male, rather than the female, becomes pregnant and gives birth to the young. On the reef, the delicate and shy seahorse has completely reversed the familiar roles of parenting. These fish form loyal, monogamous pairs, and their daily ritual involves the female visiting the male in his small territory. When they are ready to mate, the female uses an organ called an ovipositor to deposit her unfertilized eggs inside a specialized kangaroo-like brood pouch on the male's abdomen. The male then fertilizes the eggs inside this pouch, and the pouch seals shut. This pouch is far more than a simple container. It functions like a mammalian uterus, lined with a rich network of blood vessels that secrete a placental fluid. This fluid nourishes the developing embryos, provides them with oxygen, and removes their waste, all while protecting them from the open ocean. The male carries his pregnancy for several weeks before undergoing a series of muscular contractions, giving birth by jetting out hundreds of tiny, fully formed miniature seahorses into the water. The male is the ocean's most devoted father, a gentle-bodied creature that has evolved to become a living, protective cradle for the next generation. And so, our journey through the vibrant, living world of coral reefs comes to a gentle close. If you happen to still be awake, that's perfectly all right. You can simply lie back, let the music keep flowing in the background, and drift in and out of the story at your own pace. But if your eyes are heavy, let the stories of coral reefs and the gentle music carry you softly into rest. Sleep well. Good night.